Welcome everybody to our third video on vector line integrals. So let's say now that we want to calculate the line integral over c of f dot dr, where f is going to be our vector field y squared 2xy plus 1, and c is going to be now a triangle that has these vertices 0, 0, 4, 0, and 0, 5, and we want to orient that thing counterclockwise. So we've got a closed curve and we're going to go in the counterclockwise direction as we're tracing it out. So plotting each one of those points, 0, 0, 4, 0, 0, 5, we get a triangle that's doing something like this with our orientation going counterclockwise, and we can break that curve C up into kind of three natural parts along each leg: C1, C2, C3, C1 along the x-axis, C2 along the hypotenuse, and C3 along the vertical leg. And so we can do a parameterization for each one of those, just kind of again using our quick and dirty parameterization. For C1, R of t just looks like 1 minus t times our ending point, or 1 minus t times our starting point plus t times our ending point, giving us 4t0 with t going from 0 to 1. For C2, same thing, 1 minus t times our starting point plus t times our ending point, giving us 4 times 1 minus t, 5t, again, t going from 0 to 1. And C3 being 1 minus t times our starting point, 0, 5, plus t times our ending point, 0, 0, gives us a parameterization of 0 and 5 times 1 minus t, with t going from 0 to 1. And so when we calculate this line integral over our big triangle C, we can just break that up as the sum of our three line integrals over each one of our curves, C1, C2, C3. So doing each one of those independently, the integral over C1 of f dot dr, so our x values now get replaced with the x values from our parameterization. So x gets replaced with 4t, y gets replaced with 0. In our vector field, we get this expression dotted with 4, 0 for our derivative, and that's going to give us 0, 1 dotted with 4, 0, or 0 dt. So that one's 0 automatically. For C2, so what happens with C2? Well, with C2, kind of going back to our parameterization, x was going to be 4 times 1 minus t, y was going to be 5t, so when we substitute that expression in, we get 5t squared plus 2 times x being 4 times 1 minus t times y being 5t plus 1. Our derivative was just negative 4, 5 for that one. Simplifying these expressions, doing our dot product results in an integrand of negative 300t squared plus 200t plus 5 integrated over 0 to 1, which results in an integral of 5. Now for our final curve, C3, yet again, we kind of go back and look at the parameterizations of that one. So for C3, we had x being 0, y being 5 times 1 minus t. So we had 5 times 1 minus t quantity squared, 2 times x was 0, y was 5 times 1 minus t plus 1. Our derivative, 0, negative 5. Doing that dot product simplifies down to negative 5 dt, integrated from 0 to 1, just gives an answer of negative 5. So the integral over our entire triangle was just going to be the sum of those three integrals, which then gives us 0 plus 5 minus 5. Again, we get a value for 0 of that one. So geometrically, we can kind of ask the question, what's really happening here? What's necessarily going on when we're computing these things in this array? Well, the picture is kind of this. We've got our curve that's passing through here just for our r. Then we've got the tangent vector dr that's heading off in that direction. At this particular point P that we're interested in, we've also got this vector field vector that's attached to that point being our f of p. And so if we look at, well, how much of this f of p vector is kind of going in that direction? Well, one thing that we can recall is that f dot dr was going to be the length of f times the length of dr times the cosine of the angle in between. Well, this length of f times the cosine of theta is exactly the contribution of f that's in the direction of our dr. So what we can really think of is that at each one of these points along the curve, our vector field is kind of given this little push in that direction, either in that direction or maybe it's opposing that direction. And so it's contributing, either it's contributing or taking away from the direction that we're actually going. And so when we do the integral, we're just kind of putting together all of these little pushes and pulls that the vector field is giving us in the direction of the path that we're going, and the contribution of this vector field, and kind of putting all of those together gives us the kind of work or what's being contributed as the energy or whatever we want to think of in terms of this vector field doing this work along this particular path. So hope that kind of gives you a little bit of a geometric insight. We've computed a few examples, and so now I will see you guys next time.